So we'll now move to the next talk in our session given by Mark Bun, and he will talk about the equivalence between private prediction, or sorry, private classification and online prediction. Thanks, Mark.
Thanks for the introduction, Rachel. And thanks to Rachel and to Michael for organizing, as usual, an awesome TPDP program. So I'm going to be talking about some joint work with Roy Livni and Shay Moran. And so, like, 80% of this talk is going to be about definitions. So I figured I'd start by cutting to the chase. What we show in this work is an equivalence between two basic models in computational learning theory. One is our friend differentially private pack learnability, model for differentially private binary classification. And the other is the notion of online learnability, first introduced by Littlestone. And what we show is a qualitative equivalence between these two notions. So anything you can learn in one model is, in principle, exactly learnable in the other model. Okay, so to start describing these models, I'll begin with the non-private model of binary classification. And this is using Valiant's pack model from the 80s. So in this model, there's some unknown distribution over a known possible space of points, from which a learner is given an IID sample, x1 through xn, which is labeled by some unknown concept from some class of functions, big C. Okay, so think of these data points x1 through xn as these like red and green points, which are separated according to some concept C, and labeled according to which side of this half space they're in. Okay, so a learning algorithm is given this labeled sample, and its goal is to produce a hypothesis, so a belief about what this underlying concept should be. And its goal is to produce a hypothesis that's close to the unknown underlying concept, at least with respect to the distribution over samples that it was given. So we say that a learner L is a pack learner if for any distribution D over samples that it might be given and any possible target concept. With high probability over the choice of the sample, this hypothesis that it produces is going to have small disagreement with respect to the true concept. All right. Sorry, I'm having trouble advancing the slide. Okay, so paralleling John's talk quite closely, I'm also going to look at the simple example of learning one-dimensional threshold functions. So in a non-private scenario, you might be given some distribution over here, given in blue, as well as some like unknown threshold over here, so that everybody above the threshold is labeled with a negative label, and everybody below the threshold is labeled with a positive label. Okay, and it turns out that a very good learning algorithm for learning one-dimensional thresholds over the real lines is just to take hypothesize a threshold at the maximum positive example in your data set. Okay, so you can show that this is a really good learning algorithm. So it turns out that just with a constant number of samples, independent of the domain size T, you can learn a hypothesis threshold with small disagreement with respect to the underlying threshold. All right. So what this algorithm shows is that learning thresholds over any domain is possible with a constant number of samples, again, independent of the domain size. And in fact, in non-private learning, we have an extremely good understanding of how many samples, the sample complexity that's required to learn any concept class. And this is characterized by this combinatorial parameter, the VC dimension of the class. So in general, the VC dimension of a class C is at most log of the size of the concept class when C is finite. But it can be much smaller. So in particular, in this case of threshold functions, it's 1, independent of the domain size T, and in particular tells you that you can non-privately learn thresholds even over infinite or continuous domains. So the question that motivated this work is, we have such a great understanding of the sample complexity of non-private learning. Is there another combinatorial parameter that would give us a similarly precise understanding for private learning? Okay, so just to remind you how we add privacy into the picture. we're going to be studying the differentially private packed model, which was first formalized in work of Kasi Viswanathan, Lee Rasadnikova, Nissim, and Smith. And here you simply just augment the non-private packed model by requiring that the learning algorithm that you're using be epsilon delta differentially private. All right, so what's known in this model? Well, first off, a lot of the algorithms that work really well in the non-private setting fail to be private in fairly catastrophic ways. So in particular, this learning algorithm that we saw for thresholds, well, it's deterministic, so we know that it can't be like differentially private and achieve good utility. But in particular, like what it's doing is it's like spitting out a hypothesis that leaks somebody's individual information in the clear. So this is like, blatantly non-private. But nevertheless, there are lots of things we can do to design differentially private learners. In particular, this paper of Cleaners showed a generic private learner that achieves a sample complexity upper bound of log size of the concept class over epsilon. And it guarantees pure epsilon zero differential privacy. And in fact, for pure epsilon zero differential privacy, so where delta is equal to 0, we again have an extremely good understanding of the sample complexity of private learning. I won't quite go through this, but it turns out that the sample complexity of pure differentially private learning is exactly characterized by the one-way randomized communication complexity of the function evaluation problem for your class C. And in particular, this gives tight sample complexity upper and lower bound for learning the class of threshold functions over a domain of size T.
What do these pictures mean, Mark? I'm trying to connect them to the
this
the
is
map.
Alice and this is Bob. Alice, Paul, and Sideshow Bob, and they're like communicating.
Okay. Yeah. Got it. Thanks.
All right. Okay. So that's all for epsilon zero differential privacy. And you can ask, how does the situation change for epsilon delta differential privacy? And here I'll be fixing sort of like the most permissive parameters of epsilon and delta that guarantee non-trivial privacy. And it turns out that for a lot of specific concept classes of interest, there's been a lot of work designing much more sample efficient differentially private algorithms for these classes. And in particular, for the class of one-dimensional threshold functions, the sample complexity of learning thresholds with epsilon delta differential privacy turns out to be upper bounded by something like polynomial in log star of the domain size T. Okay, so with pure differential privacy, we needed log T samples. With epsilon delta differential privacy, we can get away with something like log star, where here log star is the number of times you have to take the logarithm of T in order to get down to 1. So like extremely slow growing function of T for all intents and purposes, at most like 6. And I don't know, like if you see such a result, at least if you're me, like, you would think, this has to be just like some kind of artifact of the analysis. Like there's got to be a way to improve this thing to a constant. But it turns out that this like log star dependence is necessary. That it turns out that if you want to privately learn thresholds, you have to incur some dependence on the domain size. And in particular, privately learning thresholds, as John mentioned in his talk, is impossible over infinite domains. Okay, so given this result that we at least up to this polynomial factor now have a characterization of privately learning thresholds in terms of some like interesting-ish combinatorial quantity, you can ask what is the sample complexity of privately packed learning an arbitrary concept class C in terms of the combinatorial properties of C. And I wish we had an answer to this question, but we don't. That's still like one of my favorite open questions in this area. But what do you do when you can't solve the question you really want to solve? You set your sights a little lower. So what we do in this work is we do just that. While we can't quite characterize the sample complexity of private learning, what we can do is we can delineate between when an infinite class C, such as thresholds over an infinite domain or another class defined over an infinite domain, is privately learnable using any number of samples at all. All right, so that's what we do in this work. And here's the main characterization. So what we show is that if you have an arbitrary concept class C with a parameter called the Littlestone dimension, D being finite, then the sample complexity of privately learning that class C is sandwiched between something like log star of D and something like exponential in D. So the lower bound, that the sample complexity of private learning is at least log star D, was actually shown in prior work of Alon, Livni, Maliaris, and Moran, who actually just gave a reduction to the threshold lower bound that I mentioned before. So in particular, they showed that any class of large Littlestone dimension has a copy of threshold of one-dimensional thresholds hiding somewhere inside it, and that gives a lower bound for arbitrary concept classes. So what we show in this work is a qualitatively matching upper bound, that whenever a class has a finite Littlestone dimension, it has a differentially private learner with a finite number of samples. So a corollary of this is that a concept class is privately learnable if and only if it has finite Littlestone dimension. Okay, so what is this Littlestone dimension that turns out to characterize differentially private learning? Well, to describe this, I'll get to the second part of the title of the talk, which is the connection to online learning. Now, at this point in our lives, we're all like extremely, perhaps like a little bit too familiar with online learning, but it's like worth making the precise model precise. So here it is. So this parameter, the Littlestone dimension, turns out to be best explained operationally in terms of how it characterizes the online mistake-bound model of learning. So in this model, there's, again, some known concept class C. The learner is trying to learn some unknown target concept, little c, within that class. So the way learning proceeds is in an iterative fashion through this like game between an adversary and a deterministic online learner. So in each round of the game, the adversary presents an example from the domain. The learner makes a prediction about whether that should be labeled 0 or 1 according to the concept. The adversary presents it with the true label for that example, and so on and so forth, proceeding, ad infinitum until the end of all time. And we say that a learner makes a mistake in round I if its prediction in that round disagrees from the true concept evaluation at that point. Okay, and we say that a learner L learns C with mistake-bound D if, regardless of the underlying target concept and regardless of the adversary's like strategy for producing this like infinite sequence of examples, the learner always makes a finite number of mistakes. And this number of mistakes is bounded by D. Okay, so the definition of Littlestone dimension, one definition, is that the Littlestone dimension of a class is exactly the minimum D for which there's a mistake-bound learner for the class achieving mistake-bound D. And it turns out for threshold functions over a domain of size T, the best thing you can do to design an online mistake-bounded learner is one that achieves mistake-bound log T. And this is an algorithm based on binary searching for the threshold. And I won't go into this at all, but in general, there's like one algorithm to rule them all, and that for any concept class C, there's like one particular algorithm called the standard optimal algorithm that achieves the best possible mistake bound for that class. Okay, so so just to remind you what our main result is, we show the direction that if you have a concept class C with finite Littlestone dimension, so in particular, if it has an online mistake-bound learner with mistake-bound D, then there's a differentially private learner for that class using something like exponential and D samples. So I don't have time to like give you to do like any justice at all to the proofs, but I'll tell you at least what like the main two ingredients are. So the first thing we do in order to prove this is we introduce yet another model of learning that's equivalent to these two, which is this model that we call globally stable pack learning. So here we show that whenever a class C has a mistake-bounded learner with mistake-bound D, there's a very special non-private pack learner, which is what we call globally stable, in the sense that for any distribution D and every concept in the class, there's going to be some hypothesis in that that the learner produces, which is produced with noticeable probability. So there's like something that this algorithm is like reasonably likely to produce. Okay, and the way that we prove this lemma is via like an online to batch conversion. So we like run the standard optimal algorithm a bunch of times, but instead of feeding it in a sequence of examples in an online fashion, we just feed it a batch of examples coming from the pack setting. And the second ingredient to proving the talk is a generic conversion from a globally stable pack learner into a differentially private one. So we show that, in fact, any globally stable pack learning algorithm can be converted into one that's differentially private using roughly the same number of samples. And this is not a super exciting technically in terms of like the differential privacy ingredients that go into it. It turns out to just use standard differentially private algorithms for histograms or equivalently for identifying heavy hitters. All right, so I want to wrap up just with like a couple of related recent developments and give some shout outs to other work in particular is appearing in this TPDP. So a question that we asked in the initial version of our work is whether these results relating private learnability and online learnability could be extended to multi-class classification problems, so problems beyond binary classification. And this was answered affirmatively by Jung, Kim, and Tawari, who showed such an equivalence for K-class classification and showed in one direction of the equivalence for more general regression problems. But they left open the converse question of whether online learnability implies private learnability in regression settings, which is still a nice open problem. Another nice question is what we can say about the computational complexity about these transformations. So it's known that for a restricted class of pure differentially private algorithms, pure differentially private polynomial time learners can be generically transformed into efficient online learners. But this turns out to be false in general, at least under standard cryptographic assumptions. And nevertheless, the converse direction, whether polynomial time online learners, as we discuss in our work, can be transformed into polynomial time private learners remains totally open. Okay, so I'll just finish with this slide of open questions, which I'll leave here while we take questions. I really think, this characterization that we have so far is like, primarily qualitative, and I think it just opens the door to like finding sharper and more like algorithmic connections between online learning and differentially private learning, which I think can be mined to design like interesting and hopefully also practical algorithms in each setting. And in particular, like one question I want to highlight is like, what looks like just a technical question. If you could improve our learning algorithm for arbitrary Littlestone classes from an improper learner, one which does not necessarily output a hypothesis from the given concept class, into a proper learner, then you would actually add another model to this equivalence between like private learning, online learnability, and so on and so forth, which is differentially private query release, as John discussed in his talk. All right, so thanks everyone. Happy to take questions now.
Thanks, Mark. All right, so crowd, type your questions into the chat, or alternatively, unmute yourself and just like jump out with the questions. In the meantime, I have one question which seems to be huge, and I guess has like a part of this slide, which is that you showed that the sample complexity is somewhere between log star and like exponential, and so at least we know something about kind of like when it is finite, but that's also like a huge gap. Do you have any thoughts or like conjectures as to where in that space the true complexity lies?
Great. So to some extent, this huge gap is inherent. So because of matching upper bounds for threshold functions and matching lower bounds for, well, nearly matching lower bounds for certain classes of like maximal Littlestone dimension, we know that the best you could hope to improve the lower bound is to something like log to the 1.5 of D. And the best that you can improve, log star to the 1.5 of D. And the best that you can improve the upper bound to is something like order D. So there's still like this tower gap that's inherent. But I would suspect that it is possible for the upper bound to be improved from exponential ND down to polynomial ND. I don't have like good evidence for this though.
Sure, thanks.
So
Any
this
more
in particular
questions?
motivates the question of whether we can find some other parameter, not, it can't exactly be Littlestone dimension, some other parameter that does tightly characterize sample complexity of epsilon delta learning.
Nice. Any more questions? Go ahead and just like unmute yourself if you want to ask Mark a question. And if not, we can thank Mark. Thank you very much for your talk. This was great.